Welcome to problem solving session for linear algebra. I am Siddhi Balgambore from IIT Gandhinagar, and today we will discuss problems related to the topics which are covered in this course. So we can discuss any topic which is discussed and taught in this course. Okay, so the if you have any doubt, please ask, because this session is mainly organized for this solving your doubts, and we will try to cover problems from each topic which is discussed or taught in this course. So if you have any doubt, please ask. Otherwise, I will start with the questions.
No, regarding
Yes,
this last week assignment,
yes, sir.
the last question, how to solve
Could you please let me know, sir, which assignment is it?
week 10,
Okay, week 10.
last question.
Okay, let me check. Is it related to what, sir?
It is from polynomial inner product.
Okay, okay. Let me just see. Week 10 assignment, okay. Okay, is it this ax cube plus bx square in P3R?
Yeah.
P0. Okay. So let us try to solve this one, if we can solve. Okay. So question 1 is that let px is equal to ax cube plus bx square plus cx plus d in P3R be such that p of 0 is 0 and p dash 0 is 0, and okay, and integration minus 1 to 1 mod of 2 plus 3x plus x. Okay, so we don't need mod since we are in R, and we are anyway taking square. Dx square is as small as possible. Then compute the value of 5a plus 3b plus c minus d. Okay, so first of all, since so px is ax cube plus bx square plus cx plus d, okay, such that p of 0 is 0, such that p of 0 is 0 implies ax a 0 cube plus b 0 square plus c 0 plus d is equal to 0, right? So these imply what? D is equal to 0. This is the first thing which we get from the given information. Now the second is p dash 0 is 0. So p dash 0 is equal to p dash 0 is 0 implies p dash is what? 3x square plus b or 2bx 3ax square plus 2bx plus c plus 0 is equal to 0, right? So these imply, if I substitute 0 everywhere, or 0 square 0, so this implies that c is equal to 0. Okay, so my p itself now becomes px is equal to ax cube plus bx square, right? And they have said that this integration is as small as possible. And this is part of question. Okay. So what we can do is, so we have to now solve this 5, what is value of 5a plus 3b, because c and d we anyway got to be 0 and 0. And this value of integration minus 1 to 1 2x plus 3px square dx is as small as possible. So let us try to see what it gives us. In 0 to 1, 2 plus 3x minus ax cube plus bx square, right? Dx. So which is equal to integration. Let me just take minus bx square plus 3x plus 2 dx. Okay, so it becomes what? Minus ax power 4 to 4 plus
A whole square is there. No?
o whole square. Whole square. Then what will be the square of this term? Okay, so let us calculate it. Minus ax cube minus bx square plus 3x plus 2 square. But what they have given is this is as small as possible. So I think we have to talk about Cauchy-Squarce inequality for this. So just let us check that first. What Cauchy-Squarce inequality says that this, right, is less than equal to norm of V into norm of W, right?
Yes.
So if that is the case, then inner product of this, so this is like inner product of V comma V will be less than equal to norm of V square, right? And this is as small as possible. So what can we do about this? 5a. Because this they have said is as small as possible, then we have to actually compute norm of this thing. This, let it be. What is square of this? Just calculate first the square of this term. Minus ax cube minus bx square plus 3x plus 2 minus cube plus b minus bx square plus 3x plus 2. So it is minus a into whole thing. Let me just copy this. Minus bx square into this plus 3x into this plus 2. I mean, we could have used that formula of square, but let it be now. A minus x a square x power 6 plus ab x power 5 minus 3a x power 4 minus 2a x cube plus AB x power 5, let me take this, plus AB x power 5, or if you know, just it is square plus second term square, that is b square x power 4 plus 9x square plus 4 plus all the possible multiples of these two terms. So that is 2 into first two terms is AB x power 5 plus minus 2a x power 4 minus 2a x cube minus 3 2 I mean 6 b x cube minus 2b x square, so 2b is 4b plus 6 to the 12x. So this is the square of this term, and we have to integrate now from -1 to 1, which is a bit tedious, but let us do this. So integration of this whole thing. So all the odd degree terms will go to 0, right, when we integrate. So still let me write. It will be x square x power 7 by 7 plus b square x power 5 by 5 plus 9x cube by 3 plus 4x plus 2ab x power 6 by 6 minus 2a x power 5 by 5 plus minus 2a x power 4 by 4 minus 6b x power 4 by 4 minus 4b x power 3 by 3 plus 12 x square by 2. This entire running from -1 to 1. So wherever there are even degrees, it goes to 0. So this will be 0, and rest is a square x powers, okay, a square 1 plus 1 by 7. So it will be 2 by 7 plus b square 2 by 5 plus 9 2 by 3 plus into 2 minus 2a. So it will be 4 by 5 minus 2 to the 8 by 3. That's it. So this is integration of this term. And they are saying this to be as less as possible. So if that is the case, when could this be as less as possible? So then let us just solve this, which is a square 2 by 7 plus b square 2 by 5 plus this is 6 plus 8 minus 4 by 5 minus 8 by 3. So this is a square 2a square by 7 plus 2b square by 5 plus this is 14 minus 12 plus 40 by 15. I mean, this requires some calculation, and what I mean, this will be now 52 by 15. I hope what I did was correct. And this they're saying is as less as possible. So what does this mean? Since this is norm of something, so this is norm of, this is, if we see, it is norm this is inner product of this 2 plus 3x plus px, comma 2 plus 3x plus px. If you remember, oh, it was plus.
No, it is minus actually.
Minus, okay, so I wrote the question wrong. Okay, it was minus, no? So, okay, it is correct. So, this will always be greater than equal to 0. So, the least possible value of this thing will be is equal to 0. Right, so what they are saying is then 2x square plus 2a square by 7 plus 2b square by 5 plus 14 minus 52 by 15 will be equal to 0. Since this integration minus 1 to 2 plus 3x minus px whole square dx is norm of this 2 minus 3x minus px whole square, comma 2 plus 3x minus p. We just had to use the property. So this has to be greater than equal to 0. So least possible value for this is equal to 0. Okay, so then what I will get? I hope my calculations are correct, otherwise values won't follow. But what this will be 14 into 15 minus 52 by 15. By 7 by 5. So what this will be? 60. 210 minus 52 by 15, which is 8. 15 by 15. So 2a square plus 2b square, which is 5a square plus 7b, sorry, not 5, 10a square plus 14b square is equal to 35 into this 158 by 15. And what this will be? This will be some number, and then it will give us minimum possible values of a and b. And based on that, I think we can, okay, 5a plus 3b was asked. What we had here was, okay, so 5a square plus 7 2b square. If I remove 2 from both the sides in the above term, what it will be? A square by 7 plus b square by 5 is equal to half of this will be 79 by 15. And then 5a square plus 7b square is equal to 35 into 79 by 15. And we anyway know, compute the value of, okay, 5a plus 3b. Okay. Was my calculation correct in between whatever I was doing? Here it was 3. Just a second, let me check. Mhm. Okay, I think I don't know how to do this right now, but I will try to solve the question and I will post the solution in the group, or I will add it to this file while I upload this. Is it okay for now?
Oh,
But
Okay, no
So,
problem.
okay.
No, I
Sorry
also
for
got stuck at this point only. Subsequently, I don't
okay.
proceed.
Okay. But I think it is, I think we have proved many inequalities for inner product earlier. If you remember that norm of f square plus norm of g square is equal to 2 norm of f plus 2 norm of g. I think we need to use those kind of, what I can say, those kind of inequalities to obtain this. But at this moment, I don't know. But I will let you know if
Okay.
I am able to solve this. Okay.
I asked in the discussion forum, what they told is we have to use the orthogonal projection, orthogonal complement, all these things we have to use.
Okay. Okay. Okay.
Don't know
Yeah,
how
I
to
mean, that is there because if you see, I mean, first two, for example, here 2 and 3 are there, and here px is from this.
Yeah, here actually this
Yeah,
p of x is orthogonal complement to 2 plus 3x.
yes, exactly. So we have to use those those things because
Okay.
if yeah, u is orthogonal to v, then we have this inner product property, right? I mean, we have to solve that. But I think we can obtain this. Let me, I mean, it won't be this tedious to solve. Yeah, we have to like smartly use those inequalities and we will obtain. But I will definitely solve this. And just I will add it to this miscellaneous file in like today evening or tomorrow, by tomorrow evening. Okay.
Okay.
Yeah. Other than this, is there any question? So I wanted to discuss a few questions, which I think we can.
Okay, you can proceed.
Yeah, you had some doubts, then please ask. I will try to clear those.
Now, one thing is yesterday when we were discussing this adjoint operators, no,
Mm-hmm.
whether we can consider a matrix when we were solving this adjoint, whether it will be always true. No,
Yes,
see,
if it is
always I'm
finite
telling,
dimensional, then yes, always. Finite dimensional, for example, if we are going from finite dimensional linear transformation to, because see, what we have is if T is from some V to W, then we always have this thing. Okay, if this is n dimensional, this is m dimensional, then T beta will be this m cross n matrix, and we know that the T star gamma to beta is just transpose of dagger of this matrix, the conjugate transpose. So we can always use this. But in order to do that, this V and W must be finite dimensional vector space, and we must have uh, matrix representation for that linear transformation.
okay,
Okay, so yeah, definitely, if linear transformation can be represented as this matrix, and which is always possible, we proved that if it is from finite dimensional vector space to finite dimensional vector space, we can always have linear transformation matrix, and it is easier to work with the matrix in that case, and we can definitely do this. Yes, is it okay? Is this what you
yeah, yeah,
want
yeah,
to? Yeah,
yes.
okay. Apart from this, any doubts in general, uh, or we can solve this? Yes, sir.
You can proceed.
Okay. So I just wanted
In this,
to, yes, sir.
hello.
Yes,
In
sir.
this context, I just had one small doubt. Question two that you have wrote.
Okay. Okay.
Yesterday you said that in your class you said that rank of T is equal to rank of T star
Yes.
for us. So I just thought if rank of T is less than n, then whether this holds good.
Rank of T is, you are
If
saying?
not, if it is not full rank,
Okay.
in that case, whether rank of T is equal to rank of T star.
I don't think rank of T is equal to rank of T star always. But no, it not always. I mean, um, when I say not always, I mean If it is finite dimensional, then yes, because we are just taking conjugate transpose of this matrices. So rank of this matrix is essentially equal to rank of this matrix. So rank of this is, so rank of A is equal to rank of A dagger. So if finite dimensional, then definitely it will be equal. But if not finite dimensional, then it won't be.
Okay.
Yeah.
Similarly, null space of A is also, can we say using rank dimensionality theorem, null space of A is equal
Nullity,
to,
yes. Null space,
yeah,
no. There is difference between nullity and null space. So yeah, nullity, I mean the
nullity.
dimension of null space. But no. In that case, we can't say this because, for example, rank of this is suppose A or N. Rank of this is N. Okay, but not N. Let me take. For example, in this case, T is from and T star will be from WM to WVN, right? When I'm writing these subscripts are linear transfer, what I can say, these subscripts are dimensions, then dimension of V is equal to rank of T plus null space of T star, right? Sorry, T. So this gives me rank of T to be, if I call this rank of A to be some P, then it will be N minus P, right?
Yes.
But for T star, dimension of W is rank of T star plus nullity of T. So these imply rank of, oh sorry, no, not this, nullity of T is equal to N minus P. Here then nullity of T star will be M minus P. So this, if it is not same dimension vector spaces, then it will be different. Because when we apply dimension theorem, it is applied on the domain of that linear transformation. So for T, it will be applied on V, and for T star, it will be applied on W. Is it okay?
And then similarly, nullity is understood, but how then rank we are telling it's equal?
Because it is just transpose of a matrix. In a matrix, I mean, this is finite, we are talking everything about in finite dimensional vector spaces. So rank, this is some matrix, right? Say A. Then rank of A is rank of A transpose. Right? This is true. And if we are in real vector spaces, then conjugate will be same thing. Then rank of A will be rank of A dagger, which is essentially rank of A transpose. And even in complex case, the rank remains same for a matrix, for a dagger. So that's why I'm saying the rank are equal. We are using matrix property that rank of A is equal to rank of A transpose to conclude this.
Okay, thank you.
Is it okay?
Yes, yes.
Is that okay for everyone? Or if I am saying anything, if I am mistaken somewhere, please let me know that this does not hold or something like that. Okay, next, if so, let me ask you this question that let T be a linear transformation, linear operator, let us take, then, or let us talk about A. Let A be a matrix with n eigenvalues then A belongs to Mn cross n R with n eigenvalues, then A is diagonalizable. Can someone n eigenvalues? And so what this is, so that we can take A LA from Rn to Rn, not even LA, we can just take T from Rn to Rn such that T beta to beta is A or beta to gamma. We really don't, I mean, those are all just multiplication by elementary matrices, so nothing changes much. But if this is T, then there are n eigenvalues of this linear transformation. Then is this T diagonalizable or this A diagonalizable? When I say this, I mean that whether this A is PDP inverse, where D is diagonal and P is invertible. D is diagonal, P is invertible. Any guesses for this?
No, n eigenvalue means there can be a
It doesn't mean distinct, need not be distinct. Let me write it. An eigenvalue need not be distinct. Okay, if distinct, then we know that everything is good. But these n eigenvalues are not distinct. I mean, A, we can very well take it in C, doesn't matter. They are saying that we have n eigenvalue. It means that the characteristic equation splits. It gives us n eigenvalues. It has n roots. So can we always say that A is diagonalizable?
But we should get n linearly independent vectors also.
Yes, exactly. So that is important. I mean, to have n distinct linearly independent eigenvectors. Okay, so can you give me explicit example? Because it is really important to see that how this works, that we can. I think we did not work on any example where we had distinct eigenvalues, but only one eigenvector for multiple, more than one multiplicity and something like that. So can someone give me any example, or you have you have known this, that this happens? Because we know that this doesn't happen. This is not always the case just because it has n eigenvalues, because as sir said, the dimension of eigenspace need not be equal to multiplicity of that corresponding eigenvalue. But can you give me an example? So this is false, which is okay. Okay, so let me give you the example for this, because it is really important to get that 100. Okay, then determinant of A minus lambda I will be determinant of 1 minus lambda 0, 1, 0, 0 minus lambda 1, which is 1 minus lambda and lambda square minus 0 into anything, whatever it is, plus 1 into 0 minus 0. Okay, so it is 1 minus lambda square. So this implies eigenvalues are lambda is equal to either 0 or lambda is equal to 1. But 0 has two multiplicity. 0 and 1, lambda is equal to 1. Multiplicity of 0 is 2 and multiplicity of 1 is 1. Okay, so let us try to find the eigenspace corresponding to lambda is equal to 0. Since it has multiplicity 2. Because for 1, we will anyway get at least one vector space because that's why it is an eigenvalue. Okay, so that's not a problem because multiplicity 1 will always give us one or the other eigenvector because that's how it is eigenvalue. Okay, so for multiplicities, we have to check. So since 0 has multiplicity 2, let us say, so what does this mean? That ax is equal to 0x. It means a is what? This is equal to 0, 0, 0. So this is axyz is equal to 0, 0, 0. So this will be x plus z is equal to 0. It is 0 plus 0 plus 0 is 0 is equal to 0. So it is not even doesn't make anything. So this implies x is equal to minus or z is equal to minus x. So we have y is equal to 0 and z is equal to minus x. So E0 is this a into 1 comma 0 comma minus 1 such that a in R. So dimension of E0 is 1 but multiplicity of E0 or 0 is 2. So therefore this is not eigenspace. Therefore it is not an eigenspace. Is it okay?
Yes.
Okay. So this is one thing which I wanted to discuss because we not explicitly worked on any example, at least during the interaction session. I mean, as far as I remember. And apart from this, any doubts? Not in this, but in general, if you like, after looking at this, if you want to ask any doubt related to diagonalizable or any eigenvalue related question, please feel free to ask. If not, then if you have any question, please let me know. Otherwise, I would like to discuss a few more questions. Is it okay? Do you have any doubt? So let me start with this question that let T be a linear operator on a given vector space V and let W be a subspace of V, then check whether the following subspaces are W invariant or not. Okay, so we have to check whether given linear transformation and given for the given W, whether it is. So let us take this that V is equal to P3R and T of f of x is f dash x. Okay, and our W is P2R. Okay, so our T is from P3R to P3R, and we have such that f of x is going to f dash x. F dash x means the derivative of this f, and we have to check whether this W, which is P2R, that is all the degree 2 or less polynomials, whether they form whether W is invariant subspace or not. Any guesses? This will be right, because what is T of, let F belongs to W. This implies F is of the form ax square, let me write this, plus bx plus c. Then what is T of f of x? It is just 2ax plus b, and which anyway belongs to P2R, right? So that's why it is P invariant. So that's not a problem. Is it okay? But now this, again we are in, so now V is PR. So it is all polynomials in in variable x. Okay, and now T of f of x is equal to x into f of x, and W is P2R. And so any guesses in this case?
It will be false.
Yes, it will be false. Okay, so this is not true, because when, so if we take fx is equal to ax square plus bx plus c belongs to P2R, such that then T of f of x is what? Ax cube plus bx square plus cx, and which definitely doesn't belong to P2R, because this is degree 3 polynomial. Okay, so that's why this is not W invariant. So P2R is not P invariant. Just let me write. Okay, and just to see, like, can we have a subspace such that under this linear transformation it is invariant other than 0 and whole space? Can you give me an example of invariant subspace of PR such that it is invariant? Just one.
If you take f double dash of x double,
Not for this F double dash. No, that's not. I'm not asking. I'm not asking. T is fixed. Any W. Any W.
to make it invariant,
Huh. To make it invariant. T is there. T is given. But can you give me a W such that it is invariant under this T?
ax plus bx
Ax plus.
b.
Okay. And how? So Ax plus B, when you say, then it is P1R, right?
Yeah,
Ax plus B.
which will be
Then
subspace of W also.
yes. But is it invariant? Because still our
Now if you take x f of x t f of it will be x into ax plus b, so it will be ax square plus bx. Still it is in P2.
no. When I say uh, let me write a question. Can you give me a subspace? Can we find, or this question? Does there exist a subspace of V, subspace W of V, such that W is T invariant, where or let me write PR, T invariant, where T of f of x is equal to x f of x. This is my question. So we have to find a W. And when I say W means under this T of W must be inside W. Right? So can you give me a W which is always contained in this W? Invariant subspace?
Constant.
Yes. Constant zero subspace, or how we write it, like W is F in PR such that f of 0 is equal to 0, right? Then when I take T of this f of x, then how it is? X into f of x, right? Then when I take 0 of this, if 0, or let us call this, give us some name to this, say G, then G of x, G of 0 is 0 into f of 0, right? So which is 0. So this implies this G is equal to x f of x, which was nothing but T of f of x. This belongs to our W. Okay. So yes, this subspace is actually T invariant, but this P2R was not T invariant under this T in PR. So W is T invariant. Oh. Is it okay? So we have to also choose. So if someone asks, just give you this and PTR to something, they can just ask whether this T has any invariant, this V has any invariant subspace under this T or not, and so on. So just I wanted to give idea of this. Is it okay? Any doubts here?
Here only for 0 it will work, or if I take any a, suppose f of any constant, will it work?
So you are saying f of a is equal to 0?
Not 0. If I take some a, some f of
f of 0 is a?
Yeah.
F of 0 is equal to a, but this is not then vector subspace, right?
Yeah. Okay.
Because when we add, it will be like for f and g in W, where W is f in P R such that f of 0 is a, then f plus g, when I evaluate it at a, it will be, sorry, at 0, it will be a plus a. And this will be 2a, so f plus g doesn't belongs to this W dash, let me call her W1. So therefore, this is not even subspace. Therefore, W1 is not subspace. But you can take any A here, I guess. This would work. Because when we add two terms, f of a plus g of a will be 0 plus 0, and c into f of a will be c into 0, and it will be 0. So you can vary variable here, but not here. I mean, where the evaluating, I mean, where you have to evaluate your f, that you can choose, but you can't, I guess, choose this. I mean, it has to be 0, otherwise it won't work. Even 1 won't work here. Is it okay? Because 0 polynomial does not satisfy that condition. If you take any a non-zero, so let me write this. If I write WA such that f in PR such that f of 0 is a, then 0 and a non-zero, then 0 of 0 is 0, which is not equal to a. So 0 polynomial is not in our W, which is contradiction because it is subspace, so it must have 0. I mean, is it okay?
Yeah, it is okay.
Yeah. And apart from this, so let us take this. This is a bit different, or I think second one, which we had, third one, okay. That V is equal to M2R and TA is equal to 1, 1, 1, 0, A. Okay, it is matrix multiplication. And we have proved this is also linear transformation, by the way. And W is equal to A in V such that A is equal to A transpose. So it is all symmetric matrices. So what is your guess? So just let me write how W looks like. So it is A in V such that ABCD is equal to ACBD. And so it is, if I write, it's ABBD in V where ABD belongs to R. Any doubts? The symmetric matrices. Because here A is equal to A and D is equal to D means AD in R, and here we are getting B is equal to C and C is equal to B. So we have to fix one of the variable and we have to vary the other one. Okay, so this is given. So, and so how for any, what, let me take UVWX in W or ABBD. What is T of this matrix? It is multiplication by this matrix, right? So it is A plus B, B plus D, A and B, right? And this doesn't belong to our W because since A is not equal to B plus D in general. It could be, but in general, this is not true. Is it okay? Just simple calculation, following the definitions and everything. If not, then let us solve this one. Question 4. I think, sir, you were asked the first question. I think we can get hint from this question for that. But let us see. Actually, when we try to solve problems related to inner products and other in that domain, it also depends on how the inner product is defined. For some inner product where we work with Rn or R2, those are quite easy compared to when we have to work with inner products on polynomial, vector space with polynomials and so on. So we have to find the maximum value of this. So any guesses for this? What inner product and what we will use? So we can take V to be R3 with standard inner product. Okay, then in that case, this we have Cauchy squares inequality, which states that for all v comma w in V, norm of V, norm of W, right? An inner product of on R3 is this. So we have to choose our elements to be this. If we take 1, 2, 3, X, Y, Z, then which is norm of V1 is 1 square, 2 square plus 3 square. Norm of this one is X square plus Y square plus Z square. And this is X plus 2Y plus Z mod. And this is square root of 1 plus 4 plus 9. And here we are given X square plus Y square plus Z square is equal to 1. So here I have 1. Then taking squares on both sides, I will get 14 is less than equal to X plus 2Y plus 3Z whole square. Any doubts here? So sir, when we were doing that, the square part, I think we can use such properties of inner product space where we have to smartly choose A, B's and C's, where inner product will be easier to calculate, I guess. But I will definitely try to solve that and will let you know the solution for it. But is this one okay?
Yeah, this is okay.
The next question we will solve. It is related to inner product. So suppose U is a subspace of C2, C3 defined by U is equal to span of this 10I, 111 in standard inner product. Let A B minus 1 by 2 be a basis of U perp. Then first find value of 2A and second find value of A square plus B square. Did so any so they have given that basis of U perp is this. It means this element here is orthogonal complement of both of these elements. So in that case, inner product of A comma B comma minus 1 by 2 and 1 comma 0 comma I is equal to 0. So it implies A minus 1 by 2 I is equal to 0. So this implies A is equal to minus 1 by 2 I. So therefore mod of this is, so this I can write as 0 plus minus 1 by 2 I. So that is 0 square plus square root of minus 1 by 2 square. It is square root of 1 by 4, which is 1 by 2. And the second element is 1, 1, 1. So this is A, comma B, comma minus 1 by 2 with 1, 1, 1. And this will give me A plus B plus minus 1 by 2 is equal to 0. So since we already know that A is equal to minus A, A becomes plus, then here doesn't change the value of mod A, but still. This is 1 by 2 plus 1 by 2i. Okay, then this A square plus B square is A square is 1 by 2i square plus B square is 1 by 2 plus 1 by 2i. So it is 1 by minus 1 by 4 plus 1 by 4 plus 2 into 1 by 4i minus 1 by 4. So it becomes minus 1 by 4 plus 1 by 2i. Any doubts here? Was that minus? No, plus. I hope this is okay, just calculation. So one thing, please understand that when we have vectors and we have its orthogonal complement, so we know that if V is W is a subset or subspace, its orthogonal complement will always be a subspace. Okay, so even if we take span of, so what I was saying is W is a set and W perp is a subspace, which we proved, right? That for any W perp is always a subspace of V. Okay, so this W perp is subspace and it is orthogonal complement of a set. But even if I take span of W and call this some U, this is now a subspace of V. Then U perp is actually W perp. That's what I'm saying. So if element is orthonormal to some set, then it is orthonormal to or every element, not orthonormal. If it is orthogonal to some element of a set, then it will be orthogonal to all the elements spanned by that set. I just wanted to make this clear here. And one thing which we were discussing in our, I think the week 10 discussion, and where we were discussing that if, I think it was 6, though, if let V be a finite dimensional subspace, then check for true or false that U is a subspace of V, then U is equal to U perp. If you remember, we were discussing this and we were kind of stuck because we know that if U is equal to U perp, then U is a subspace. But if U is a subspace, then can we always say that U is equal to U perp? So this happens only in case of finite dimensional case and not in general. Okay, so I will try to prove it for finite dimensional case. And I also have an example for this, but that example is kind of non-trivial based on whatever the topic covered in this syllabus of this course. But still, let us try to prove this, that U is a subspace, but it is subspace of a finite dimensional vector space. Then U is equal to U per prop. That is double orthogonal complement of a set is equal to itself. So, any guesses for this, that how can we proceed with this? Or any proposition which you would like to recall from the lecture? What, any guesses that how shall we proceed with this? Okay, so let me just start with this. That let V be this is proposition proved in the lecture, dimensional inner product space, and U is subspace of V. Let V belongs to V, then V can be written uniquely as V is equal to U plus W, where U is in U and this W is in U per. This is proved, and this is followed by the fact that if W is subspace of V, then if W has then we can extend its basis to a basis of V. And then when we take orthogonal complement, Gram-Schmidt orthogonalization, then those W1 to WK forms basis for W, and WK plus 1 to WN forms basis for W per. Okay, so using that, we obtain this thing, that given any U, given any element V in V, it can be written as U plus W, where U comes from U and W comes from U per. That is orthogonal complement. Now, can someone proceed that how can we try to prove that U per perp is U per per? So this proposition is the hint.
Now, if we take in R3 three vectors,
Okay.
in that three are orthogonal vectors,
Yes, sir.
then first two we can take it as a subspace, and third will be the orthogonal to the first two, right? So
Yes, sir.
So the third vector will be orthogonal of that will be the U itself, the other.
Yes, because then we are like switching between the vector spaces. Yeah. But how to like write? If I give you anything, so you are saying that if my W is W1 to WK, and then what you are saying is that W per, so V is W1 to WK and WK plus 1 to WN, right? Then W perp is,
WK plus 1 to WN.
yes, span. In fact, I made a mistake here. W perp is span of this thing, right? So you are saying that so if I call this U is equal to W per, then W per will
be
have
yeah,
span of this W1 to WK.
yeah,
That's right.
yeah,
And which is W, because
yeah.
this span of W1 to WK is W. This is okay, but what if we don't have any information about the basis of this thing? Yes, this is perfectly fine. But for this, we need to have now basis of W. But can we always say this without having the information about U? that u per is u always. I don't know what are the basis and anything. Just the fact that any element v is this. Like one more way of proving the same thing, but using this now. Because see, what we are doing here is we started with the basis of w and then we are taking w per. But see, what I was saying is this w per may have some basis and okay. This is fine.
But I can always find orthonormal vector from that Gram-Schmidt.
That, yeah, Gram-Schmidt, yes.
With that, I can find the W1 to Wn.
Yes. Yeah, we can extend this to ortho, yes, but how can you prove? So let me ask you this. I mean, even I am now. Suppose W perp is span of this WK plus 1 to Wn. Okay. Okay, W perp is some space. Okay. Then you are saying that I can always find span, I mean, this. We don't know what is the basis of W. Okay. We just know the basis of W perp. Okay. So then W perp is span. So I will extend this to V is orthonormal basis span of WK plus 1 to Wn, and this will be W some U1 to Un. Then W perp is generated by span of this U1 to Un, right? But how can we say that this is equal to W? If I don't know the basis of W, I just know the basis of W perp. I mean, am I making sense here? How can we say this? I mean, this is actually true, but this way we can't, I mean, have any concrete argument, right?
Yeah,
That
what I thought was, suppose I take in R3 A00,
Mhm.
0B0, and 0,
Yes,
0,
sir.
C, three
Mhm.
vectors.
Yes.
Then I take a subspace as A00, 0B0 as the
One
uh,
W and W perp will be this 00C1. Yes.
0, C.
Yeah.
Then I thought is the orthogonal of that will be A00 and 0B0. So
Yes.
I thought in that way.
Yes. But that is like particular example. But in general, can we always do this? Because see, proving that this will form W is a bit different. This definitely forms W per, but is this does this vectors or not n k always span W again? So it will be yes, but we have to give some argument for that. And let us start. So we have to prove that U is a subspace. Then we have to show that U is equal to U per. That is exactly what we will be proving here actually, that this is actually W. So how to do this? So we will first prove that U is contained in U per, right? So let U belongs to U per. Then what does that mean? Then for all, oh sorry, not U. Yeah, U, then U comma V is equal to 0 for all V in U per, right? Then by definition, U belongs to U per, right? Because it is its inner product with all the elements from U per is 0. So U is anyway contained in U per. Is it okay? This statement which I just wrote here. Since U is orthogonal to every element of U per, it belongs to orthogonal complement of U per. Is it okay? Then by definition, U is in U per.
Yeah.
Yeah. Okay, so this is there. So we got that U is contained in U per, right? Now we have to prove the definition, the other inclusion. So now let us take V in U per. Okay, then this V also belongs to our vector space V. Then from this proposition, what we have is then V is equal to U plus W, where U belongs to U and W belongs to U per. This much is clear by above proposition. Then since V is equal to U minus U plus W, this implies V minus U is equal to W, which belongs to U per. Is this okay?
This U and W are vectors in U and U per. Right?
U is in U and W is in U per.
Okay.
What I'm saying is now W is in U. V is what? V minus. So from here, I get V minus U is equal to W. Since W is in U per, this implies W is equal to V minus U is in U per. Now is it okay? V is equal to U plus W. Then V minus U will be W. And since W is in U per, then this W is equal to U, V minus U is in U per.
No, okay. Here this we are writing V equal to U plus W, right?
Yes,
I-
yes, yes.
No,
Using this
U.
proposition.
Yeah. No, but there only what that U plus W means. We are adding two vectors or what? What
Yes,
actually?
yes, yes. It is addition of two vectors.
Okay.
Where, I mean, we are just representing it, where U is in from U and W is in from U per. And this representation is possible due to this proposition that for any given V, we can write it uniquely. This U and W are unique such that U is in U and W is in U per. Is it okay? So I'm just writing this. So now again note that we know that V belongs to U per. That's what we started. Okay. And U belongs to U, right? So this implies U also belongs to U per. That's what we proved here. If I call this star by star. So I have V in U per, U in U per, and since this is vector subspace, V minus U will be in U per, right? Is this okay? We have this, we started. This is given. This by star, we just proved. Okay. Then what we have, if I call this 1, if I call this 2, this implies this V minus U is such that V minus U belongs to U per and V minus U also belongs to U per. And what does this mean? If an element is belong to U perp and U perp, both of them, then what can we talk about this element? This implies this V minus U belongs to U perp intersection U perp, right? And what it will be? This implies V minus U has to be 0, right?
Yeah.
Yes. Because otherwise for any non-zero element, this is not possible. Because for any non-zero element, its inner product with itself is always positive. Okay, so if an element belong to this both sets, then for them it has to be is equal to 0, right? Because this now V is coming from U and it's now coming from its orthogonal complement. Then it has to be 0. But we know this V is non-zero if V is non-zero, then this inner product is non-zero, which in fact positive. So that's why this doesn't hold. Okay, so it has to be 0. If an element belong to a subspace and its orthogonal complement, then it has to be 0 if it belong to both of them. Okay, so this imply what? That V is equal to U. But where this U belongs to? U belongs to U, right? Because we started with U. So this implies V belongs to U. So where we started? So V was my element from U per. So therefore V was my element from U per. And what we arrived at, that V belongs to U. Therefore this U per is actually contained in U. And from what we have, this implies that U is equal to U per. Okay. Any doubts here? We were just playing with where the element belong in U per, or in U and so on. It was not much of a calculation, but to check where certain element belong or not. Is it okay? Or any doubt in any step here?
Can you slightly go up?
Yeah.
In this, first we assumed V as well as U in U per, right?
Not assume, we got that. I mean, we arrived at this conclusion. This is anyway we started with. And U we got from this. That U is in U, then U is subset of U per always. So my U was in U, so it is by definition is in U per.
Okay.
Then their subtraction will be in U per because U per is a subspace. And from here, this W, we got that it is in W per. And from here, we got that it is in W per. These two steps.
Okay. Okay.
Yeah. This is really important because this happened only because we could write this. And that's why we arrived at the conclusion that, okay, this element is in both U perp and U per, then it has to be 0 and V is equal to U. And since U is in U, V has to be in U and so on. So is this okay now? So for finite dimensional case, yes, this hold that if U is a subspace, then U is equal to U per. But this happens only when we have finite dimensional thing on V. This is not in general true for infinite dimensional vector space, infinite dimensional inner product space. And you can find counter example very easily. Or yes sir, you are trying to say something?
No.
Okay. Okay, so I mean, can you come up with a counter example in infinite dimensional space where the subspace is not equal to its orthogonal complement? Okay, so I would like to give this example because it's good, but the thing is, you have to work out the details of it. And we can start with this space. So V is subspace of all the sequences such that summation k from 1 to infinity, we will work with real, okay, is less than infinity. It is such that the summation of this xi square converges. So this is vector space where you will find a counter example. So can you give me a subspace of this vector space? So this is vector space, okay? Why? Because when you add these two things, so and here inner product will be summation xk comma yk is summation k from 1 to infinity xk yk. Okay, this is inner product. And you can check that this forms a vector space. That's not a problem. But can you give me a subspace, assuming that, yeah, this forms subspace and this is the inner product space, inner product which is well defined. That when I say well defined, this means that this inner product itself is also less than less than infinity. I mean, in finite dimensional vector spaces or the vector spaces which we were working will not give us counter example. I mean, I couldn't find any in those vector spaces which we saw in the lecture so far. But yes. So we can take this. W is a sequence such that, so let me write this. Xk is what? It is a sequence, right? So it is of this form, goes up to infinity such that xi is equal to 0 for all I greater than equal to j, where j is 0. So it is like, sorry, j belongs to some n. So it is like set of all sequences where the tail of a sequence is constant equal to 0. That is, it is sequence like 1, 1 by 2, 1 by 3, 1 by 4, and after 5 everything is 0. Or 1, 1, 1, 1, 1, 1 up to 100 and everything else is 0. And this W is definitely belongs to this V, right? Because W has only, so in short, like it is xk such that only finitely many entries are non-zero, rest are zero. Then this is under this V. This W is contained in this V because these are finite many numbers. Then summation of these finitely many numbers will be some finite number again. Then we claim that this W perp is actually zero. Okay, and if this claim holds, if claim hold, then W perp will be entire, W perp will be V perp, and which will be V, right? Because zero perp is always entire space. But you can say that this is properly contained in W. Okay, so here W is not equal to W perp. But now we need to prove this claim. Proof of claim, that is W perp is equal to 0, is, since this is sequence, note that all the elements of this form x, k, I, where 0, 0, 0 for I in n, 0, 0, 0, 1, 0, 0, 0, ith position. This belongs to V. Okay, because summation x, I, k from 1 to infinity, it is just 1 which is less than infinity. So this belongs to W and V. Okay, because only finitely many, that is only one entry is 1 and rest are 0. Okay, so therefore we have this. Then if we take any y, k in W per, then it is what? It is sequence of the type y1, y2, y, I, and so on. And it goes. It could have all the entries 0, all the entries non-zero. We don't care about that. It is just a sequence such that xk comma yk is 0 for all xk in W, right? But we know that this xki's, since xki belongs to W, then if I take inner product of this xki with this yk, what this will be? It is summation of xk I yk, I from 0 to infinity, which is just yk, right? And then this implies that it is 0. Sorry, it is just yi. Okay, because here all the xi's are 0 apart from the ith entry. So this is yi and it has to be 0. And this is true for any I in and we can choose as inner product of xki comma yk is yi, and this is 0. So this imply what? That all this yi are 0 for all I in n. So this imply this yk which we started with is actually 0. So all the entries of this sequence which we started is 0. Therefore, W perp is actually 0. And this xki which I wrote here, okay, actually this form basis for this W if you check, but that's okay. Do you understand this? That this W perp is 0, and then this implies that W per will be entire V, and this is definitely not equal to W per, because there are infinitely many more elements which are in V but which are not in W. Okay, this is counter example for infinite dimensional case. And why I'm not going into the details of proving this inner product and everything is because we need to know the information about how the series converge, what are the conditions for series to converge, and so on. So this is kind of analysis part, so which I don't want to, but I didn't also want to like leave. I mean, I wanted to give the example for this. So yeah, this is the example which we have. Okay, if you get any simpler example, please let us know in the discussion forum. But yeah, this is the example. So this W per perp is equal to W happens only in finite dimensional case, because we have many good results when we work with finite dimensional case. Is this okay? Any doubts? I mean, at least you got the whole that, yeah, in this case, W per perp will be 0. I mean, W perp is 0 and W per perp will be V, and which is not equal to W. Yeah. This we know for any V, 0 per is entire V. Okay? Because inner product of 0 with anything is 0, so it gives us entire vector space. Is it okay? Okay, so let me move to next question. I don't know question number, but let us call this question 7. So let T be a linear operator on a finite dimensional inner product space V over R. We denote by T the null space of T. Then check whether true or false. First is that for all V in V, T star TV, that adjoint of T star TV, is 0 if and only if T of V is 0. And when we say T of V is 0, we mean that T is a 0 linear transformation. Any guesses for this? Yesterday, if you remember, we saw this, that Tmi comma V is equal to 0. Then it is false that this is false. Okay, that if then T is equal to 0. This is false. For all V, then T is equal to 0. This is false. So What are your guesses for this? Okay, so let us start with the first one. So we have this thing and we have to check whether this always happens. So let V be in V. Then what is inner product of T with T star TV? What this will be?
So the inner product of TV, comma TV.
Yes, this is inner product of TV comma TV, right? But what this is? What is this, by the way? What is the value of this thing?
Since given, if we take TV equal to 0,
No. See, T star TV is anyway given 0. Okay, so T star TV is equal to 0. This implies V into T star TV is 0 because we are then taking inner product with this, right? Given that. Okay, so from here that you said that T into V star TV is 0. This implies that this, as you said, it is TV into TV is 0. So this implies that TV has to be 0 by the definition of inner product or the properties of inner product space, that it has to be 0, and this is true for any V in V. Okay, this is
Ma'am,
like
how?
for all V. Sorry, sir.
Hello.
Yes, sir.
Ma'am, how it's comma TV inner product?
This, this,
No.
then
That step two. No. V
this.
inner product of into no above that, just above TV comma TV. That comes from the first line.
Here,
Inner product of yeah. How that comes from its previous?
because we know that, right? That V comma, I mean, this is property of adjoint.
Yes, that's true.
Property of adjoint or adjoint property. So what we have here is, what is V comma T star TV? It is V comma T star of TV, right? And what is this?
Okay.
TV comma TV. Okay,
Okay.
it is kind of composition. So yeah, we are considering this as an element now. And then,
Okay.
yeah. And this is by the property of inner product. So therefore, TV is equal to 0 for all V in V. So therefore, this T is 0 linear transformation. Okay, so the first implication is true. And the second one is anyway trivial, right? Because TV is 0, then compose it with any other thing. It will always give me 0. Okay, so the other implication, since TV is equal to 0, then T star TV is anyway 0 for any given V. So this was not, I mean, it was not needed. So is it okay? TV is 0 for all V. For all V in V. This apply this for all V in V, and this is it. And now this which we discussed yesterday and which we end up saying that it is true, that let beta be an orthonormal basis of V, then T beta beta is equal to T beta beta dagger. And what are your actually guesses for this? Actually, yesterday we said that it is true. But like the inner products and symmetry and everything is okay. But let me try to write this for let n is equal to 2 or dimension of V is equal to 2. Then it will be what? By our given information, let me just write this T beta beta. It's TV1 comma V1, right? And TV2, TV1 comma V2. And here it is TV2 comma V1 and TV2 comma V2. Okay, this is what we know because beta is orthogonal basis of V. Then I take dagger of this beta to beta dagger. The real and everything will give me the so it is conjugate, but conjugate will be same thing because we are in real. So forget the conjugate, but we have to take transpose of this now. So it will be what? TV1 comma V1, TV1 comma V2, TV2 comma V1, sorry, yeah, and TV2 comma V2, right? And even by symmetry, I switch this VI's and I mean by symmetry. Okay, so transpose is already taken. And this is not equal to this thing. Okay. I mean, these two things are not equal. That TV2 comma V1, this is not equal to, in fact, TV need not be equal to V2 comma TV1. Okay. So these two things are not equal. But can you give me explicit example where T beta beta is something and its dagger is not equal to the matrix? I mean, when we try to write it in the general form, we can see that this is not equal. Oh, let me write this. No. Meanwhile, you can think of an example. Note that in general, TV2 comma V1 need not be equal to TV1 comma V2. So can we come up with an explicit example for this? So when we are saying that we want to find an example for this, we just have to give an example of a matrix where matrix and is kind of transpose. Since we are in real, the conjugate won't make any difference, but the transpose of a matrix is not the matrix itself, but it has to be okay. So we can simply take this linear transformation. Okay, so we can take this T from R2 to R2 and beta could be this our standard basis. Okay, then this T beta beta will be what? Sorry, let me write t first, such that t of x comma y is going to minus y comma x. So this t beta beta is 1 comma 0 is going to 0 1. Yeah, 0 1, and 0 1 is going to okay. Then what is t beta beta dagger? It is just transpose of this matrix, right? 0 minus 1 1 0 conjugate transpose, which is just this 0 minus 1 1 0, and this is definitely not equal to t beta beta which we started with. Okay, so this statement is actually false. I have added this in the notes, but yeah, this is false. So what we discussed yesterday was had some error. So yeah, this is the correct one. That this need not always be the case, because this doesn't always happen. And this is the example. And this is not very this is not any matrix of some speciality, but you can take any matrix, any linear transformation, such that it's real linear transformation where the transpose is not equal to the matrix, and it will serve as counterexample for this statement. Is it okay? Okay, then if there are any doubts, please let me know. Otherwise, we'll move to next question. And this is question which I would I don't know, maybe question 8 or something like that. So for a given subspace W of V, find the dimension of W per. Okay, so we have to find dimension of W per. We will be given the information about the subspace of vector space V, and we have to find the dimension of W per. Okay, so let us take this simple example. Let us take V is equal to M2R. Okay, and W is this A in M2R, such that trace of A is equal to 0, and inner product of A and B is trace of B transpose A. Okay, so we have to find dimension of W per. So how will you find the dimension of W per? If I give you this information, what will be your plan of action to find the dimension of W per? Will you like go ahead and solve the to find the basis for W per and then count the element and then conclude that this will be the dimension of W per, or what? Okay, so remember this. This is a corollary proved in, I think, week 10 syllabus. Then that it is dimension theorem for orthogonal complement. Okay, and it is like that if let V be a finite dimensional vector space, let W be a subspace of V, then we have this dimension of V is equal to dimension of W plus dimension of W per. And this is quite evident from the fact that when we have basis for W, we can extend it to the basis of V. And when we take orthogonalization, the V1 to VK forms W1 to WK forms vector space for basis for W, and WK plus 1 to N forms basis for W per. So it follows directly from that proposition, and we have to prove this. But so from this, what will be the dimension of this W per? So for that, we first need to find the dimension of W. Okay. So dimension of W is what? What is W first of all? W is A in M2R such that trace of A is 0. If you remember, I actually solved this. What will be the basis of W per for 3 cross 3 matrices? If you remember it at the end of the notes of week 10 interaction session. Okay. So it is A, B, C, D in M2R such that A plus D is equal to 0. And so this is A, B, C, D in M2R such that D is equal to minus A. So in that case, it is A, B, C minus A in M2R such that A, B and C in R. So what is dimension of W? So dimension of W is 3 because we have 3 linearly independent. Okay, so if I want to write the basis of W, it is this 1 0 0 minus 1 0 1 0 0 0 1 0 0. Okay, and dimension of W then becomes 3. So therefore, by what I can say, let me call this so by above corollary, dimension of W per will be dimension of V minus dimension of W. So therefore, dimension of W per will be, what is dimension of V? In fact, dimension of V, we know that dimension of V is 4, and we got that dimension, it will be 4 minus 3, then it is 1. Okay, so this corollary actually saved a lot of time for us to explicitly finding that, because see, the inner product was not quite easy if you see. Okay, so similarly, if we have this that V is P3R and W is 1 comma 1 plus x comma 1 plus x minus x square. Okay, and inner product is f comma g is equal to integration minus 1 to fx Okay, ft gt dt. Okay, this is inner product, which we already know. Then if someone tries to ask you find the dimension of W per, then finding W per in this case, if I explicitly try to find W per in this case, it will be quite difficult. Okay, but not this, it is span of this thing. Okay, so clearly dimension of W is 3 in this case, and we know dimension of P3R is 3 plus 1, which is equal to 4. Okay, we discussed this, that dimension of PNR is n plus 1 because it is n degree polynomial. So degree 1 to degree n plus constant. So it gives us n plus 1 element in the basis. So therefore, dimension of W per is dimension of P3R minus dimension of W, which is 4 minus 3. Therefore, dimension of W per is just 1. Okay, any doubts here? Okay, so please remember this theorem, because if you don't and if you go and try to solve explicitly what is dimension of W and so on, then sorry, what is the basis of W and then count, it will be difficult because inner product could be given any difficult. For example, in this case, finding this trace of B transpose A will be summation of AI, like let me just write, like for if A is Aij and B is Bij, then trace of B transpose A is summation Aij into Bj, Bij, I comma j from 1 to 3. Okay, so which is something very tedious to deal with. Okay, so this is not always easy, but still I have given the explicit proof that how to find the basis of this W per in notes of week 10. Please go through it just for having the feel that how to find W per of given linear inner product space and so on. But using this corollary, if we are only asked about the information of dimension of W per, then we can immediately use this corollary and we can obtain the dimension of W per. Okay. Any doubts or any question or anything which you would like to ask? Yes, sir.
This week assignment, I had one doubt. There is a question called the same adjoint only. T, if T star T equal to 0 implies T equal to 0. What actually that means?
Okay. Which
Only,
question? Week 11.
yeah, week 11. There is
Week
a
11. Okay. Assignment. Okay.
it is third question.
Yes, sir.
What
Yeah.
actually the T star T equal to 0 implies T equal to 0?
Oh, so T star T equal to 0 means? So T is anyway linear operator. So
Yeah,
T is from V to V and T star is from again V to V. So when we write this T star T is equal to 0, it means T star TV is equal to 0 for all V in V. So it is 0 linear transformation. So what they are saying is if T star T is 0, then T is 0.
okay. Because that
Okay.
previously we proven that if TV equal to 0, T star TV equal to 0. Already we have proved.
Okay, I mean right now, right? We just
Yeah.
proved this. T star TV is 0 if and only if TV is equal to 0. So you can take hint from this and mark your answer accordingly. Yeah. But apart from that, I mean, And similarly, I mean, the next question is about T star, TT star. TT star is also the same thing, that TT star, it is equal to 0 means TT star is from again V to V, such that TT star of TT star of V is equal to 0 for all V. Yeah.
Okay.
Okay. Any further doubt, whatever we discussed or in general?
Ma'am, I have a basic doubt actually.
Yes, sir.
What is adjoint of a polynomial? If a polynomial is defined in a real field, whether the adjoint will also be same?
So adjoint is defined for a linear transformation. Okay, so adjoint is defined for a linear transformation. So
So
if
in case how whether the function of the linear transformation also they give?
yes, sir. I mean, if they are talking about adjoint, they must give you a linear transformation. Yes.
For a case of matrix, adjoint we define as that
Orthogonal, I mean, conjugate transpose.
conjugate transpose. Yes.
Yes.
Similarly, for polynomial, anything is there. For polynomial, can we define adjoint that way?
Okay, sir. So let me tell you this thing, that if T is from P and R to P and R, right?
Yes.
Okay, this is finite dimensional.
Okay.
And then this T will have some matrix representation. Okay. Then T star by definition again will be T star from beta to beta. This will be again T beta to beta. Yeah, dagger. But this is for finite dimensional case, and how the linear transformation is defined and so on.
Okay, ma'am.
I mean, it depends on how, I mean, when I write this, I'm taking standard linear transformation and so on. I mean, so actually this entirely depends on how your inner product is defined, how you're taking complement and so on, because this is not true in general, but it depends entirely on how your inner product is.
Okay, ma'am.
But if you are given any linear transformation, then finding its star in general is difficult, but it is easy in case of PNR. So what you can do is you have this. I mean, this is true for actually Rn to Rn and not in general. So if your inner product on PNR to PNR, if you take, and your inner product of polynomial, for example, if I have a naught up to an x power n, comma b naught up to bn x power n, such that inner product is just summation a naught, ai bi I from 0 to n, then this will be true. But if your inner product is something like that, integration minus 1 to 1 f of t g of t dt and so on, then this need not hold. What orthogonal complement? Because this, when I write this inner product of t, for example, f comma tg is equal to t star g comma f, the inner product here plays role. How we are defining this inner product and so on. So in general, we can't have, for matrix, we can take transpose and everything, because on matrix, we know we are taking standard inner product and so on. So there we can directly do this, but this in general cannot be obtained. I mean, just taking transpose, I mean, dagger or conjugate transpose won't give us.
Okay.
Yeah. So if the T is defined on PNR to PNR, but inner product is this, then we can have this. But in general, inner product, we can't.
Okay.
Yeah. Any doubts now? I mean, further doubts? Oh, sorry, I must be F, G. Any doubts? If not, then just a suggestion from my end that if you are giving exam, please try to memorize the inequalities or identities which we prove for inner product and norms. That will be handy in the exam. And apart from that, if you have any doubts, please post the question in the discussion forum and I will try to solve that question if possible and will post the answer. I mean, add the answer to this file itself. And we will discuss exercise or problems related to week 12 syllabus in next week. Same time, Saturday, 3 p.m. So next week, yes, sir.
No, next week class will be there.
Yes, next week it will be there. So this was miscellaneous class where this was general for the entire syllabus. Next week we will have class from 3 to 5 and we will discuss problems related to week 12 especially. So we did till week 11 yesterday and next week we will do it for week 12, yes. So week 12 and that will be most probably the last session for, I mean last live interaction session, yes. So if you have any doubt, please bring next week. We will try to solve them. Yeah. If there are doubt, please let me know. Otherwise, we can end the session. Yeah. Okay, I assume there are no doubts. Okay. See you next week then.